Just reminding you that at some point we need to do that. Should we get started here? We're going to crank through the rest of section 1.1, and we'll do 1.2 and call it a day. I have some time at the end to kind of get started on your stuffs. Deal? Cool. All right. Start this thing up then. Okay. So we started this last time, right? I can't remember where what slide we left off on. If anybody, we did this page though, right? Okay. We did this page?
Yeah.
Okay. And probably on this page where we stopped?
No, this is where we stopped.
This is where this is the page that we had where we stopped. Okay. That's fine. So again, talking about SI units, all of our SI units would be metric units. One of the advantages of metric units are that, well, aside from time anyways, are base 10. So we can use these prefixes to indicate like a factor of 10 difference. So like a centimeter is, 1 times 10 to the negative 2 of a meter, or 0.01 of a meter. I had to think there for a second. Everybody's okay with metric system naming? At least these 6 or whatever should be, I would assume from your science class, pretty familiar looking. Okay. We also have derived units, so that's a unit that's the product or quotient of 2 or more base units. So like area is the product of 2 length units. So example, meters squared, meters times meters. Or volume is the product of 3 length units, like meter times meter times meter, or meter cubed. Velocity is the quotient of a length unit divided by a time unit, so like meters per second. In our textbook, they write, instead of doing division, they do a negative exponent. Probably for typesetting reasons, it's easier to typeset. If you wrote like meters over seconds, that's fine also. Like, doesn't have to be using negative exponents, whatever, means the same thing. I think it's purely like, it's cheaper to write it, to have a textbook printed, that you don't have to also typeset fractions in if you don't need to. I think it's purely an ease of typesetting, whatever. An acceleration is like your rate of change for velocity, so it's a velocity unit, meters per second, divided by another time unit, so meters per second or meters per second squared. And then density is a mass per volume. So it's a mass unit, like kilograms, divided by a volume unit, like meters cubed. With these units, we are also going to be interested in converting between units. Again, this is something I expect we're pretty familiar with from our chemistry or science classes in the past. But we'll run through it once more just to make sure. So an example, if we're just converting between 2 length units, for example, between centimeters and inches, we know that 1 inch is 2.54 centimeters. So when we set up our conversion factor, the unit on top needs to line up with the unit on bottom, and we multiply across. Everybody feels okay doing this? The place where students often make mistakes is when we have to convert between a derived unit. So if I have 10 square centimeters, I need to do that linear conversion twice because my unit is centimeters squared. So for that to cancel, I need to do centimeters conversion twice. Does that look familiar, guys? Again, if you are into the whole brevity thing, you could put a parenthesis around one of these and write squared on the outside. That's okay too. I typically write multiple sets of them because I just don't want to make a goof up and forget to do the squared when I type into my calculator or something. And then if it's a volume, we're going to need to do that linear conversion 3 times because a volume is a cubic unit. Oops. Oh my God. There we go. Again, I'm going to make mention of this because it's a super common mistake when I ask you to do this on the quiz or test. I bet a third of you still goof this up. So I'm making a point to sit here now for an extra moment and just kind of like point out to you that this is a place that's very easy to make a mistake and forget to do the multiple conversions. Just as a trying to be really transparent that this will be something you have to do and it's easy to make a mistake on even though it's easy to do. So just reminding you. Yeah, Geraldine.
So like for like the square units, is like the final like unit inches squares?
It'd be inches squared, yeah.
Okay.
Yep, because you have inches times inches, so it'd be inches squared. Or this one would be inches times inches times inches, so inches cubed. I guess we could make an edit to this and add in the units there, but yes, that would be the case. All right. The next thing we'll talk about here is approximation and error. When we talk about approximation math, in this mathematics class at least, we're talking about rounding. So when we talk about rounding, the way that we're going to be rounding is the same method of rounding you're probably the most comfortable with, where we pick the digit we're going to be rounding to. You look to the digit to the right. If that digit's 5 or bigger, you round up. If that digit is less than 5, we round down, right? So the question that we're left with, though, is how do you select the digit we want to round at? Everybody feels okay about this type of rounding? It's like your elementary school rounding, right? Okay. So how do I select where to round? We're going to be using significant figures, right? Okay. I know, it's fine though. So question for you before we talk about what a sig fig is. You've seen this in science classes before, right? What is the purpose of a significant figure? Why? What is it telling us? So you have to remember that this is a part of a science class, right? Well, it's communicating more than that, actually. So you have to remember that this is being done with a measurement in mind. So if I measure something to be 5.24 liters, and I split that into 3 pieces. So I split it into 3 different batches, right? Or sorry, let's say 5.17 liters, and I split into 3 batches. And I write down that I have 7.12333333333 liters. That's implying to the reader that has read my work that I initially took a measurement that was accurate to the 100th place. I would have used some graduated cylinder or something. And then to split it, I used some new tool that was all of a sudden accurate to 10 decimal places. I don't even know what kind of instrumentation I'd be using to do that accurate of a measurement, but that's garbage. All I did was use the same graduated cylinder I used to measure the first stuff out, right? So it tells you the level of accuracy that the tools you use to make the measurement, it tells you about the tool you use to make the measurement. And by doing mathematics, like adding, subtracting, multiplying, dividing, I can't somehow make my measurement more accurate than what it started with, right? That's the point of significant figures. That's what it's trying to accomplish. It's communicating to the reader what level of accuracy in your measurement did you have based on the tool that you used to make the measurement. Okay? Now, in this sort of math class, we're not actually going to really be doing, like, we're not going to be doing measurements and like doing experiments like you would in a chemistry class or a physics class or something like this. It's not what we're doing. It's going to be abstract. But for the most part, in this class, you can report your answer in kind of one of three ways. If there's not instructed via directions, you can report an exact answer. So if it's a terminating decimal, you just list you can list the whole thing. Or you could write it as a fraction, or you could write it as like in exact form, like 2 times the square root of 3. Or you can write it as a number rounded to 3 significant figures. Or the directions may ask you to do something specific, like round it to 5 sig figs, or to the nearest hundredth, or to the tens place, or something. So it'll either give you specifically where they want the rounding done, or you'll have the option of giving an exact answer or a rounded to 3 sig figs place answer. Is everybody okay with that? So let's talk about what a significant figure is, because if we're going to be asked to round things to 3 sig figs on occasion, I should want to know what those are and how to kind of figure that out. So examples of significant digits. Any non-zero number or non-zero digit is significant. 1, 2, 3, 4, all the way up to 9. Any leading zeros are not significant. They're considered like placeholder zeros. If you wrote the number in scientific notation, they would go away. That's how you can tell they're not significant. Trailing zeros are the tricky ones. If there's a decimal point in your number, your trailing zeros are significant. So 123.00 has 5 significant figures. When I look at that number, that tells me that when I made the measurement for 123.00, I had a tool, an instrument, that was accurate to the hundredths place, right? That tells me something about it. Now, numerically, the number 123 and the number 123.00 is the same number. But those tell me 2 very different things about the tool I would have used to make that measurement. One of them is only accurate to the ones place. The other is accurate to the hundredths place. So you kind of see what I'm driving at? Okay. Now, if there is no decimal point, like 12,300, your trailing zeros are not significant. So the decimal point is the key there. Okay, if the decimal point is present, trailing zeros are significant, all of them. If there is no decimal point present, no trailing zeros are significant. Once again, if you rewrote it using scientific notation, those ones would disappear. With the decimal point, if you rewrote that using scientific notation, they should remain. And then your last type of zero is the sandwich ones that are in between a non-zero digit. All sandwiched zeros are significant. So if you have any amount of zeros between non-zero and non-zero, anything in between, whether there's a decimal point in there or not, all those zeros would be significant. Does this sound familiar? And then the last piece of this, when rounding with significant figures, in this class, because we're not actually doing an experiment, in this class, the only time we're going to do your rounding is on your final answer. None of your intermediate calculations should be rounded. Only the final answer. So if you're doing this in your calculator, you need to make sure you're storing your you're using your previous answer to do your next calculation, or you're doing it all in one line. But you can't say, like, I can't say this and go, okay, 1.72, and then add 4 to it. That won't fly, right? what I have to do is take that one and then add 4 to it and then round. Right? You have to keep all the decimal points for your intermediate steps and only round at the final. You guys get what I'm saying? And again, for the most part, like, that's probably habit for a lot of us, but for a class that's kind of punishingly specific, I want to make sure I'm real clear as to like the expectation. You know, in many math classes, it wouldn't matter. Here, we're going to care. Because part of the course is like understanding how to round. All right. So once you've done some sort of rounding and reported a rounded answer, there is some level of accuracy that we've given up, right? When you look at a rounded answer, it's implied that there's some bound to that. So if I rounded up, there's some minimum number that this could be. Could have really been that I rounded up to the final. Or there could be some maximum answer that I could have had, actual value that I had, that I rounded down to a rounded answer. So there's always an upper and lower bound associated with any rounded answer. It's kind of like a confidence interval. If you guys are into like politics and the pollings, they always have a like margin of error, like a confidence interval. It's kind of like that. So let's look at an example. Let's say we have the number 5. That has 1 decimal, or is just rounded to the ones place, right? Now, to get to 5, we could have rounded up from the smallest possible number we could have had that rounded up to 5 would have been 4.5. And the biggest number we could have had that rounded down to 5 would be just the first number below 5.5. So like 4.999999 repeated, right? So the way we would write that would be with like an inequality. We'd say that that measurement that we rounded to 5 was somewhere between 4.5 and 5.5, equal to 4.5 but not equal to 5.5, right? So keep in mind that the type of inequality I'm using there is really specific, right? The round up should be or equal to's, and the round down should be less than's. The only time that switches if you're dealing with a negative, right? Because just everything is kind of reversed. But I don't think that we'd be asking you a question about bounds of rounding for a negative answer, since you don't get a lot of negative answers in actual measurement. It's a weird result. How much do you weigh? Negative 4.6 pounds. That diet's going really well. Ha 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 ha. All right. Yeah, and note the inequality symbols. Okay. So the bounds that we write would depend on the precision of that rounding. So if we take the number 5 and say that's precise to 0.1, so the tenths place. So really when we talk about 5, we're really talking about 5.0. Yeah.
How come it's less than or equal to 4.5, but it's not? No, it's greater than or equal to 4.5, but it's not. It's equal to on the other side.
On the 5. Okay. So if this number is 5.5, it would round up to 6. So it can't include 5.5, right? It has to include the first number less than that.
Okay.
And the easiest way to write that is just strict less than 5.5. If this number is 4.5 exactly, that rounds up to 5. We want that one and anything bigger than it. Does that Okay. All right. So if this is precise to the tens place, we need to rewrite 5 with a tens place. So 5.0. Now we have to think about, okay, what's the smallest number that would round up to 5.0? 4.95. And the smallest number that would round down to 5.0? 5.05. Actually, the first number less than that, though, right? So we'd write it as 4.95 less than or equal to x less than 505. Does that feel okay? Notice this is the same question as before. It just worded differently. What I'm trying to do is just show you that like it's still the same problem regardless of the wording. Yes, sir.
So it's just like specific to like the decimal place.
Yeah.
So, like, it's like the top, it's like that.
Yep. If it was nearest thousandth or something, then it would be, you know, be talking about the number 5.000, and then you'd be looking at the fourth decimal point. But yeah, that's the whole idea. Again, pretty easy, but you have to understand like what we're asking for here, right? The verbiage matters. It's not a difficult process, but you have to understand what we're talking about, right? And I'm trying to give you like the context of what is this really asking for, and how to think about it in a way that's like, oh yeah, okay, this is easy to understand. Since there's really no calculation to speak of. And again, we talked about the inequality difference now a couple times. Okay. The other thing you've probably done in your science class is talked about percent error. So say you're in a chemistry class and you're trying to determine like how much acetaminophen is in like your Tylenol. So you read from the label on the package, it says there's 200 milligrams in there or something. Like that's the exact value. Now you crush it up and you mix it in with a solution, you do a titration and you do a calculation, you come up with, okay, I calculated 198 milligrams. That's your approximation based on your experiment. So your percent error would have been the difference between your approximate and the exact divided by the exact. We'll take the absolute value of that because the error is kind of a positive number only, and then multiply by 100 to get a percentage. Does this look familiar? Have we done this in our science class? Many of us shaking heads saying, I've seen this calculation before. Again, do you need to memorize this formula? No, it would be given to you. The trick is you have to remember A and E, which one is the approximate, which one is the exact. It gets confusing because some kids will see E as estimate instead of exact and goof it. But you'll get the formula. You just have to remember what stuff means. Everybody happy? Yeah, I'm waiting. Would you like an appetizer?
Sure.
We're out. Get it? Because I'm waiting. So I'm pretending to be the waiter. Make sure you tip your staff, though.
I will.
Okay.
When I get money.
When you get money. Yeah. Blah. All right. It didn't matter.
Are we gonna be using OneNote? Like how we did it last year?
We'll do it for the homework turn-in. A lot of my notes are PowerPoints because, like, they're so wordy, you know.
It's wrong.
12:40 is the end of this class.
Thank you.
Yeah.
Oh my god. I'm gonna die.
You're okay. You're not going to die.
Yeah, I wrote that.
All right. We're going to run through section 2 here as well. Section 2 is just a review of some like algebra 2-ish exponent rules. So recall that an exponential function is something that can be written of the form y equals a times b to the x, where a is a non-zero real number and b is a real number greater than 0 but not equal to 1. Now remember, the reason why we don't allow a to be 0, because if it was, then the whole thing just is equal to 0, and that's a constant function. That's not exponential. We restrict b from being 0 or 1, because if b is 0, the whole thing's 0, same problem. If b is 1, 1 to the x is still 1, and then 1 times a is still a. That's a constant function. That's not what we want. And we say b can't be negative, because that x can be any real number. Specifically, it could be things that are fractions with even denominators, which is like an even root. I know if I take the square root of a negative or any even root, that's an imaginary result. It's undefined. So this thing would have infinitely many discontinuity, and it's just a gigantic mess, and we don't want to deal with that either. So that's why those extra criteria are there. That b has to be greater than 0 and not 1. Okay. Oftentimes we'll refer to that a coefficient as the initial value, because if I plugged 0 in for x, I'd have a times b to the 0. B to the 0 is 1, which is just equal to a. Oftentimes the x variable in an exponential function in the real world is time. And at time 0, that would be the initial value for your function. That's kind of where the name comes from. The b is referred to as the base of the exponential. So every time that x increases by 1, the f of x will change by a multiple of b. Right? So the y value is basically multiplied by b each time x increases by 1. Now that doesn't mean that the y value is going to increase, right? If b is greater than 1, yes, it increases. If b is between 0 and 1, like 1/2, the y value would decrease, right? Difference between exponential growth and decay. Does that all sound familiar? I think you probably do that we do that in regular trigonometry. AP guys, do you do exponential and logarithms again in AP pre-calc? Yeah, okay. And then a key feature of all exponential functions is as x approaches negative infinity, the exponential function approaches 0, right? So as this value of x becomes a very small negative number, the negative sign in the exponent moves the b to a fraction. So if I have a fraction that has a really big exponent, and that's a really big number, if I take something and divide it by something really big, it goes to 0, right? If I look at like 1/2, 1/3, 1/4, the decimal decreases for each of them until it gets to basically 0. So the limit notation we'll use to represent that is just the limit as x approaches negative infinity of f of x is equal to 0. And I think AP guys, you guys write your end behaviors with limits. That looks like a familiar notation anyway. Good. All right. So when we evaluate an exponential function, what we really need to make sure that we're careful about is that we're following, yeah, Paulie? Sure. Is that we're following the order of operations. So if I have a function y equals a times b to the x, I have to make sure I deal with that exponent before I multiply. So in other words, you might think of this, if we really wanted to add a lot of parentheses to make the order of operations super duper clear, as a parenthesis, parenthesis b to the x parenthesis, right? Where we're going to do that power of b strictly before we do the multiplication of a. Now that's a lot of unnecessary, like we have the order of operations for a reason, so we don't need 10,000 parentheses. But just to do a reminder, it's easy to get carried away and be like, 2 times 3 to the x is 6 to the x. All right. So let's run through just a couple of quick examples. So if we have y equals 3 times 2 to the x, and we have x equals 2, so if I plug 2 in for x, what do I get here? 12. Very good. Everyone first down when I asked the same question, they're like, "Oh my god!" It's 8 o'clock in the morning, and just like mental math we're not ready for that. So we plug 2 in for x. We have 3 times 2 squared. Remember, 2 squared is 4, and 3 times 4 would be 12. Everybody's cool? Okay. Or not, but like you understood what we did there, right? Even if like, boy, that was quick, you guys, I'm not sure I can do that in my head that fast. It's okay. Not an expectation that you're able to do mental math quickly or effectively. If I plug 0 in, what are we going to get? 3, very good. Again, that's just the definition of our initial value, but you could also think about plugging 0 in for 2. 2 to the 0 is 1, and 3 times 1 is just 3. And again, I wrote here anything to the 0 is equal to 1. That's not true, though, is it? There's one exception. 0 to the 0 is indeterminate, not equal to 1. If you're also in the calculus class, that becomes a major point of emphasis in the not too distant future. For the 2 people that are in the room that are smiling at me now. Okay. What if x is negative 3? What are we going to get there? 3/8. Very good. So if I plug negative 3, and remember the negative exponent makes a reciprocal, so I have 3 times 1 over 2 to the third. 2 to the third is 8. 3 times 1/8 is 3/8. Again, don't have to be able to do this in your head. You could certainly write down steps if you need steps. No big deal. This is just a chance to review some of our exponent rules, right? It's more of what I'm doing here. All right. You ready to get for the fun ones? No? Okay. Too bad. What if x is 1/2? Yeah, the 1/2 makes it a square root. So what would our answer be? 3 root 2. Very good. Yeah, so the denominator of our fraction in the exponent gives us the index for our radical. And we just call that 3 root 2. If this was on an IB test, you could have also taken 3 times the square root of 2 in your calculator and rounded it to 3 sig figs, unless the directions asked explicitly for the exact answer. Everybody's okay? Okay. How about this one? It's not just negative 2. Let's run through it. This one is like, it has so many steps, it's probably not realistic anybody's doing this in their head. 3 times 2 to the negative 3/2. So get rid of, you will evaluate the negative sign, so make the reciprocal. Now I'm going to think about 3 over 2 as 3 times 1/2 and separate it that way. So 2 to the third is 8, and the 1/2 is a square root. And then the square root of 8 is, if I simplify that, 2 root 2, right? Because I can think about 8 as 2 times 4, and the square root of 4 is just 2. And then what I still need to do, rationalize the denominator. So I'll multiply the top and bottom by root 2, and I'll end up with 3 root 2 over 4. Not probably realistic anybody was going to do that in their head in the amount of time I gave them. If I let you sit there and really like work on it for a minute, you probably could have certainly written it down and gotten there, but combined a lot of exponent rules in there. So let's take a moment and just kind of run through those exponent properties that we've seen before. So if the base of my exponential is the same and I multiply them together, the base stays the same, but we add the exponents. Or if the base of the exponential is the same and we divide them, we'll subtract the 2 exponents, but the base stays the same. If I have the product of 2 numbers and I raise it to a power, that power applies to both factors. Likewise, if I have the quotient of 2 numbers and I raise that to a power, that power applies to both the numerator and denominator. Although this rule also needs one other little criteria. What does this also, when does this not work? If b is equal to 0, right? Because then you have undefined, because you have a 0 denominator. I guess this one fails to work if a is 0, right? So again, the negative exponent makes a reciprocal, right? And then don't forget you can use it in reverse, where if the negative exponent's in the denominator, you can just move it to the numerator. It's a helpful reinterpretation. Everybody so far so good? Look familiar? You have exponent of an exponent where the exponents then multiply. And then you have the radical property where a fractional exponent, the denominator, becomes the index for the radical. Now, if this is not a unit fraction, the numerator becomes the exponent on the a. Everybody's okay there? And then we have the last one, a to the 0 is equal to 1. Assuming that a is not 0, right? Is this all, those are your basic exponent rules. Again, it's probably been a minute since some of us have seen all of these or thought about them. I know we're coming off a summer where I'm guessing we didn't do a ton of math over the summer. That's okay. This is me just doing my due diligence and making sure that like we're all kind of on the same page here. Again, these are things that I would never ask you to like write them down, but surely you should have these memorized at like what you can do and not do. Okay. That was a fun transition. Solve the equation. So if I'm solving an equation, basically I want to start with the reverse order of operations, right? So I'd look for any addition or subtraction to undo. Well, there's no addition or subtraction in this problem. Then I look for multiplication or division to undo. Well, I see I have this times 20 out front, so I'll divide both sides by 20 to start. Oops. Now from here, there's kind of 2 separate approaches I could take. One of them is I could use a logarithm since I'm solving an exponential equation. What logarithm would I want to do to both sides of this equation to solve it in the most efficient means possible? Log base 1/2. Very good. You want the base of your logarithm to match the base of your exponential. So I could do log base 1/2 to both sides. Or, in this case, I could try to rewrite both sides so the base of the exponential matches. So I notice over here I have 1/2, over here I have 1/4. I can rewrite 1/4 as a power of 1/2 pretty easily, right? 1/4 is just 1/2 squared. And now if the bases of my exponentials match, I can just set the two exponents equal to each other and then multiply both sides by 3 to get 6. Oops. That flew off on me faster than I wanted to. Now you could use a logarithm in one shot and do the same thing. You get to the same spot. Or if you're unsure on how to do this, if you're taking like an ACT or something, the other alternative is I can take out my graphing calculator, take the left-hand side of my equation, put in y1, the right-hand side of the equation, put in y2, graph it and find the intersection. If it's a multiple choice test and all I care about is the answer, boy howdy, that works. If you're ACT bound here, get one more crack at that bad boy. That's a nice tip that you can take in because you get your graphing calculator, and boy, that's a powerful tool. Yeah, and if we want to check our answer, you could certainly plug that 6 back in and you end up getting 5. Not necessary to check an answer for an exponential equation because you can't get a extraneous solution there. Since the domain of an exponential equation or exponential function is all real numbers and the domain of a linear equation is also all real numbers, can't get extraneous. If it was a logarithmic equation, you would get one possibly, since the domains are different. That is it for us for today. So that's sections 1.1 and 1.2. If we look at My Notre Dame, I've updated the schedule for the week after that, our first day, so I knew what I got through. So your assignment for sections 1.1 and 1.2 are right there. That's also an assignment on My Notre Dame, although I named the assignment just like chapter 1, problem set 1, and then the description has the numbers on it because sometimes the name can't hold all the page numbers and everything if I try to name it that way, so it's not always convenient. If you look at your textbook, what you're looking for, and we go to section 1.1, you're scrolling past all the example things. You don't have to do any of those. What you're looking for are the exercises, which are in green. So here's exercises for chapter 1.1. Notice it's starting on page 10 as per my description. The unfortunate part is that's actually page 18 in the PDF. I don't know what to tell you. It's the way the cookie crumbles sometimes. Any questions about any of that? Yeah, Joey. Yeah, so the back of the textbook has all the solutions, I think, although the editor was pretty terrible, and I think that frequently there are mistakes. Let's see, back of the answer is 526. So 534 would be, so you go back and check all the answers are there. And you're free to do that. In fact, it's encouraged. So this will be Sunday's homework check, or homework set will be these problems. On Friday, remind me first thing and we'll show you guys and talk about how to get your homework into the OneNote to turn in. If you want to write stuff in, you're welcome to write stuff into the OneNote. If you want to do it on paper, do your homework on paper, and we'll talk about how to get it from paper into the OneNote in class on Friday and kind of walk you guys through that so that we'll have a chance to do it before it's due. But I figure we'll wait till Friday to do that explanation. So if you have it done, your example of getting a picture into OneNote takes care of getting your homework into one. It's like a one-shot deal. Any other questions for me? As you're working on this stuff, If you decide like this is a gigantic hassle using this PDF, I want a textbook, let me know and I can issue you a textbook. I have lots of copies. But you guys can spend the remainder of our time here working on your assignment. Knock some of that out. Sound good? All righty. I'm be done talking. Well,